All right, we're going to talk about different ways to find the volume. So what I have here is a 3D printed tetrahedron. Has anybody ever used the 3D printers? How does it work?
It's like plastic, like strings kind of, and then it goes back and forth until it makes the shape you want.
Does that make sense, everybody? Have you all seen a 3D printer? I'm going to pass this around. Please, this sounds stupid, but you're not going to believe me and you're going to test it. But the corners on this are really sharp. But what I want you to look at is one of the faces. If you look carefully, you can see all the microcosmically small layers that are used to make up this equilateral, or actually it's a tetrahedron. Okay. Now I was going to print a solid one, but it requires too much plastic, so I just did the frame. But the way that works is it stacks layers on top of each other. And the reason I chose that versus, let's say, a cylinder, because I could have 3D printed a cylinder, but a cylinder is not very interesting because it's just circle, then another circle, then another circle, and next thing you know, you have a cylinder. The difference with that tetrahedron is that each layer, the size of the triangle changes. Okay? And we're going to be looking at those kind of three-dimensional constructions. What happens when you try to build something out of cross-sections, which is exactly what that 3D printer does, but the size or the shape of the cross-section is changing over time. Okay? And on a 3D printer, you can print just about anything. You could print a tetrahedron. You can print an infinite number of things. Cindy, what are you printing? Are you doing caterpillar, bumblebee? Caterpillar.
Yeah.
Right. So Cindy, can you talk a little bit about what you're doing?
Well, we're making an autonomous project where we're just like making a thing that like moves with different cams.
Yeah, so she's doing, I went online and found a pattern for that and just started the 3D printer going. She's actually designing a caterpillar that when you put all the pieces together, it moves. And so she's building each of the components, so you printed, I didn't see all the components, but you've got, how many pieces do you have to make up the
It's
caterpillar?
like 40, it's a lot.
Okay. And then she's building a puzzle and it'll eventually move. But each one of those things is printed using layer upon layer upon layer. Anybody not? So how do we do that? Well, it requires calculus. The cylinder doesn't require calculus because we're just adding up a bunch of circles. This, however, the size of the triangle changes at each layer. So how does that happen? All right, this is called cross-sectional. It's a variation of disk method, but it's done using cross-sections. We've got only two things to do today. Number one is find the volume using cross-sections, and number two, you should be able to relax. Some of you should focus on number two. Okay, so talked about all this already. Let's go to this guy and show you what it looks like. This tetrahedron is a fairly complicated build. It seems simple. I'm taking a tetrahedron and putting taking an equilateral triangle, then a smaller triangle, then a smaller triangle on top of each other. Okay. We're not ready for this yet. But I do have a couple examples of what it looks like. So we're going to have to decide two things. What shape is the base? So this one has a base that's a triangle. And then you have to decide what are you going to stack on top of it. Okay, so this one's it's not quite doing what we need it to do. This will make more sense. I'm going to start with a circle. I'm going to use a circle as a base, but I'm going to stack squares on top of it. Are you with me? So the squares are going to be coming up out of the board. Just to get an idea of what it looks like, I'll try to do it as like a 3D model. So I'm going to take that, and then I'm going to have a bunch of segments going along there. And on top of each of those segments is going to be a square. Okay. So what's a square? Okay, I'll ask you. Where's the biggest square, and where's the smallest square? Tom?
The biggest is in the middle, and the smallest is at the sides.
Good. Okay. If you can't see that, you get an idea of something like that. This pink square is the largest square you can get because it's smack dab in the middle. And as you move further out towards the black square, it gets smaller and smaller and smaller until we actually go to R, where it has a square from calculus. You'd have a square with an area of 0. Okay. So what we're going to do is that. And again, since this is calculus, we're going to take that infinite number of squares, sandwich them together, and get a three-dimensional figure. Okay, now the question is, this is the hardest part, you watch that square go through the path. Can you visualize what that shape is going to look like. So I'll show you that in a second. But try to visualize in your brain what that shape is, the final three-dimensional object is going to look like when it's done tracing. And I'm not even going to ask you to try. I'm not even going to ask you to try and describe it because it's just too bizarre. Got an idea? Does it look anything like that? Okay, so that's a cylinder with that funky curved parabola kind of looking thing carved out of the top of it. Okay, so what can we change? Well, let's stay with the circular base. Hold on, I gotta make sure that stops. So there we go. Let's stay with the circular base, but let's stack equilateral triangles on top. Same idea, drop it to make it look 3D. There's where all the equilateral triangles are going to be. If I show you what 4 of them look like, they look like that. Small one out on the end, biggest one in the middle, and then sweep it, and you get something like that. Same question before. Can you visualize what the three-dimensional figure looks like? I'll let it go once more, and then I'll show you. Okay, you got it? Looks nothing like a cylinder.
So tens.
Kind of. But these sides are curved. It's not like a traditional pump tent. Would be a cool tent. Okay. Let's see. What else can we change? Let's change the base. So now I'm going to use a right triangle as a base. And I'm going to stack on top of that right triangle some semicircles. Something like that. And that's pretty much a giveaway of what we're going to see. We end up with something that looks like half of a cone. And we're going to be able to find the volume of every one of these figures. The nice thing about it is you only need to come up with one thing. That one thing is the area of any one of these cross sections. At any point in time, can I write a formula for the area of that semicircle, or that isosceles, or that equilateral triangle, or that square, etc., etc. Okay? I think that's all. Anything on we got this. That's not very interesting. We did that already. This was, I don't know, what is this one? This is, I think, isosceles triangles. Yeah, it's not really exciting. It looks like the other one. Okay. So let's talk about the math here. I'm going to start, well, this is what we're going to need. We're going to need the area of one cross-section. It's not a numerical value, it's an equational value? That made no sense whatsoever. It's an equation to represent the cross-section. And it's going to be determined by the shape that we're sitting on top of. So we're going to start with a very easy model. Show you what that looks like, and then go from there. So the first one is pretty close to what a 3D printer would do. What's the graph of x equals y squared look like? Say again? Good. Parabola on its side. What's the difference between x equals y squared and y equals the square root of x? Aren't they the same thing?
No.
Why not?
One doesn't have like a negative region.
Good. Yeah. Square root of x is just the top part. This, we want the non-functional thing to do the problem. So I'm going to use this as a base. Sideways parabola. The big, bold, black segment is the shape that I'm stacking on top of this. And the shape that I'm going to use is a rectangle. But from that picture, you have no idea that it's a rectangle. It could be anything. Triangle, semicircle, whatever. Because it's sticking up out of the board. Is everybody visualizing what's going on? When I'm done with this, the reason I chose this one first is because it's closest to what a 3D printer would do. Because what I'm going to end up with is all of these parabola-shaped things stacked up on top of each other. And the reason that happens is because I fixed the height at 2. That doesn't commonly happen. But for this one, for the first one, I wanted it to be pretty simple. Okay. So I need to demonstrate that I know that that's a rectangle other than the problem. So on top of this base shape, I'm also going to do this over on the side, the shape of the thing that's stacked on top. You'll notice the bottom of that rectangle is a big, fat, bold line. That big, fat, bold line on the rectangle matches the big, fat, bold line on the base. this big fat bold line on the base has a length of 2 times the square root of x. Does everybody understand where that came from? If not, speak now. We're good? Okay, good. It's 2 times because this would be the square root of x, that's the square root of x, that's 2 square roots of x. There's my entire formula right there. Done. That's the area of any one of those rectangles at any point in time. And I'm taking rectangles starting at 0, which would be the smallest rectangle, all the way out to 9, which would be the biggest rectangle. Problems? Easy derivative to take. Sorry. Easy integral. Hard derivative to take because it's an integral. So easy integral to take. I don't even know if I don't think I even did the work. So not relevant. Everybody understand the concept before it gets a little nastier? Questions, concerns, anything with a good cause? Beautiful. Let's do something that's more traditional cross-sectional area. So like the ones we just looked at, we're going to take an equilateral triangle, stack it on top of a circle. So it's just like one of the things that I showed you. Circle with a radius of 4. Therefore, what's the equation of the circle? I have a picture, by the way. What's the equation of that circle? Nobody remembers the equation of a circle?
X squared plus y squared equals 2.
Close.
X squared minus y squared equals 2.
No, you're right. X squared plus y squared equals 16. It's r squared.
Yeah.
Okay? So, this puppy is x squared plus y squared equals 16. Okay, we can work with that. I chose, well, I didn't choose. The problem says I want my triangles to be perpendicular to the y-axis. So I've got that big fat bold segment in there. Which means it's horizontal. Should I be working in terms of x or in terms of y? Y. So this point is going to be something, comma, y. And what is that something? That something would be the square root of 16 minus y squared. And in fact, it would be negative. But we can put it anywhere, so we'll just consider it positive. It'll make our life a little bit easier. Even though it's down below the x-axis, it could be anywhere. So we'll talk distance here, which would make it positive. And why do I care about that? Because that tells me that distance. That distance is that distance. Therefore, I can come up with that whole distance by doubling it. Which means now I've got a triangle sticking up out of the board on top of that big honkin' segment there, which would look something like, where is it? There it is, that. Where the base of that triangle matches the base on the circle. Now you have to go back to geometry. I need to find the area of an equilateral triangle knowing only the base. Does anybody happen to remember the formula for the area of an equilateral triangle? I know some of your geometry teachers taught you, but that doesn't mean you remember it. Tom? I think you're the only one I... You know what I got in geometry. Christian also. Christian, you remember? Caroline, you also. I guess there's more than I got. I'm getting old. I forget things. No? Don't remember? Okay, so it's not the end of the world. If you don't remember, I assume you know enough geometry to find the height of that triangle. Is that a safe assumption? Okay. Well, I'm going to save you the hassles, and I'm going to refresh your memory on the formula for the area of an equilateral triangle. It's that puppy. You might want to jot that down. It'll save yourself a lot of hassles. S is the side length. S squared square root of 3 over 4 is the area of an equilateral triangle. Only equilateral triangles, not isosceles or right triangles. So that means the only thing I need to figure out now is what the area of that triangle is, which is a plug and chug. Take this 2 square roots of 16 minus y squared, put it in there for S, I get that. That seems very ugly. However, it will simplify nicely. Because 2 squared is 2 squared is, here we go. Wow. And the 4's cancel, so we get to that. One last question. What are my limits of integration? I'm taking those big, fat, bold segments from what to what? Somebody answer, because I'm not giving it to you. -4 to 4. Is there another way to do it? No. Okay. There is. But I think I did it from -4 to 4. So I get that. Square root of 3 is a constant. I move it out in front. I have a nice easy integrand. So I can take the antiderivative of both of those. Plug and chug, get some ugly numbers, but it works out nicely, and I get an answer of 147.802. Like a lot of these revolution problems, a nice, well-drawn sketch of what's going on will make your life a lot easier. You want to sketch the base, and you want to sketch the thing that's stacking on top of it. Those things that are being stacked are usually going to be squares, equilateral triangles, or semicircles, but occasionally some crazy things pop up like isosceles right triangles. All kinds of fun stuff like that. Okay. Problems? Beautiful. That's a cross-section of... That's the Millennium Falcon from a movie called Star Wars. I don't know if anybody's ever seen it. No? Okay, well, you should maybe watch it sometime. It's pretty good. You what?
I saw my very first one last year.
Shut up.
I've heard, like, obviously I've heard, but I've never seen them before.
Which one was the first one?
The one where Kylo Ren dies.
That's the first Star Wars movie you've ever watched.
And I had, like, yeah. My friend, like, dragged me to it. I was like, I don't want to see this because I've never seen the rest of them. She's like, you'll get it eventually. And I was
No,
like,
you didn't.
No.
I had no idea
I
who
had
those
like a
people
seizure
were.
watching it. The lights are so bad.
Wait, isn't that the most recent?
Yeah.
That's the last one.
Yeah.
I haven't seen the last one yet. Thanks for spoiling it. No, I'm kidding. I haven't seen it, but I don't really care. Okay.
Is the neutral?
Discard.
Wait.